If you're trying to get into building your own synth modules, there's a very basic question you'll have to answer right away. How are you going to supply power to your circuits? The easiest and safest way would be to use batteries. And while I strongly recommend you start out with those, especially if you're new to electronics in general, at some point you'll probably want a more permanent solution. But this is where things potentially get dangerous. There's a rule that every layman should strictly adhere to. Never mess around with mains electricity. The voltages coming out of your wall can easily kill you if you make a mistake. That's why building a power supply completely from scratch is off the table for anyone but the professionals. What we can build, though, is a PSU that relies on a professionally built wall wart. These have a bunch of security measures baked into them that ensure that you won't get fatally zapped if you mess up. Also, they scale the mains voltage down to a much lower, less dangerous level. Now, you might say, if the wall wart is scaling the voltage down for us already, what else is there to do really? Well, to answer that, we'll have to talk a bit about different kinds of wall warts and power supplies. The most common example would be an AC to DC adapter. These are the ones you use to charge your phone, for example. They take high voltage alternating current electricity from the wall and supply low voltage direct current power to your device. If you don't know the difference between alternating and direct current, here's an easy way to conceptualize it. Imagine we have two pipes filled with water. In this first one, the water is constantly flowing from here to here. That's what we call direct current. In the second pipe, the water is basically staying in place, but it's moving back and forth at a steady rate. This is what's known as alternating current. A synthesizer usually runs on direct current. So why can't we just use a simple AC to DC wall wart and call it a day? Well, there's two main reasons. The first one is not critical, but definitely a drawback. Most AC to DC adapters these days are what we call switched mode power supplies. I won't go into detail on how those work. Let's just say that they generate a lot of high-frequency noise, which then would creep into your entire set of modules and ultimately your mix's output. But second, and more importantly, such an AC to DC adapter will only give you two distinct voltage levels to work with, a high one and a low one, usually called positive and ground. Most analog synth modules need three distinct voltage levels though. A high one, a medium one, and a low one. Positive, ground, and negative. Because of that, using such a simple DC adapter is pretty much out in our case. So what's the alternative? As far as wall warts go, there's also AC to AC adapters. These take the voltages from your wall and scale them down without changing the way the current flows. Okay, but didn't we just say that our modules need direct current? Yes, but we'll worry about that in a bit. First, let's take a closer look at the voltage output of such an AC to AC adapter. That voltage output, like the voltage coming from your wall, will look like this. It's a sine wave with, depending on where you live, a frequency of 50 or 60 Hz. That means that the voltage will swing from high to low, either 50 or 60 times a second. The interesting thing for us is that with AC electricity, we usually conceptualize it as swinging around a ground level voltage, which would make anything above this line a positive and everything below this line a negative voltage. But how exactly can a voltage be negative? The key to understanding this lies in the fact that voltages are always relative. So to measure a voltage, we always need a point of reference, a different voltage that we decide to call 0 volts or ground. Let's go back to our water pipe example. For our direct current scenario, we simply said that the water is flowing from here to here. For that to happen, the pressure on this side needs to be higher than the pressure on this side. So if we now decide to call this lower pressure level here 0, we can go ahead and measure the difference between the two levels. Whatever that difference is will be what we call the higher pressure level. So in effect, we decided that this level over here is neutral, while that one here is positive. Okay, but what about negative pressure levels? The concept is exactly the same. Imagine we first lower the pressure here to match our neutral level. This means that no water will be flowing in our pipe because it's now in a state of balance. But if we keep lowering the pressure, our flow will begin to reverse its former direction. So instead of flowing towards the neutral level, it will flow away from it, because the pressure here is below the neutral level. And that means that it's, by definition, negative. So with our AC adapter's voltage output, the same idea applies. We simply decide to call this line in the middle 0 volts, and then we get positive and negative voltages in relation to that line. Where the DC adapter could only supply us with 2 distinct voltage levels, here we get a huge variety of them. Which is great, but also not exactly what we want. We need to find a way to transform this into something like this. 3 steady voltage levels. Okay, so we're back with the question we stashed away earlier. Because turning this into this basically means turning AC into DC, just with 3 instead of only 2 voltage levels. Luckily, this is not all too difficult. There's 3 main steps we have to take. The first one is what's generally referred to as rectification. This means that we simply take our AC sine wave, cut it in the middle, and then separate the top and bottom halves. To do that, we'll be using something called a rectifier diode. Rectifier diodes differ from small signal diodes, which you'll probably use in most other projects, in that they're able to pass a lot more current without burning out. This is important here because we don't want our power supply to go up in flames if we plug in too many modules. Okay, but what does a diode do again? If we go back to our water analogy, let's imagine we place a one-way valve between 2 adjacent pipes. This valve will only allow water to flow in this direction. If we reverse the flow, the valve will simply block and the water stops moving. A diode does exactly the same thing in an electric circuit. It only allows for current to flow in one direction, blocking the other. So if we take our AC sine wave and we feed it into such a rectifier diode oriented like this, we should be able to basically erase the bottom half, leaving us only with the rounded peaks up top. This is still pretty far away from a clean DC signal, but one step at a time. To try this out, I'll be using this 12 volt AC to AC wall wart, a 1N4007 rectifier diode, and to be able to see what's going on, an oscilloscope. First, let's figure out how to connect the wall wart to our breadboard. The plug fits into a standard socket that looks like this. Solder 2 wires to it and you're good to go. But wait, there's a problem right away. How do you differentiate between the 2 wires? Our oscilloscope needs a ground connection to be able to measure anything. With a DC power source like this battery, you can easily identify the 2 poles by looking at the labeling. But sadly, we have no such luck with our wall wart. And that's because there is no positive or negative poles with AC, since they are constantly switching positions, so to speak. If we go back to our pipe example, you'll remember we said that the flow is changing its direction many times a second. This essentially means that the pressure on this end is rising and falling, while the pressure on this end is falling and rising at the same time, kind of like a seesaw. So which wire do we attach to our oscilloscope's ground connector? This might sound strange, but it doesn't matter. Everything will work out the same if we choose either of them. And that's, again, down to the fact that voltages are always just relative. Think of it like this. Imagine we have 2 points next to each other, constantly moving up and down, just like our pressure levels. Now, from our perspective, it looks like they're both moving. But if we were able to take one of the points' perspectives, it would seem like only the other point is moving. So if we pick either of those points as our point of reference, that will be where the neutral position is, no matter what happens around it. And same applies to our problem with the 2 wires. Whichever we choose to be ground will be ground. This is even true for our battery. If we decided that the positive pole is now our ground, the other pole will sit at a negative voltage. But back to the world of AC. I'll just pick this wire to be our ground and connect it to our oscilloscope. To be sure this works, let's first try and look at the full sine wave. For that, I'll just plug the other oscilloscope connector straight in here. As expected, we see a nicely rounded sine wave. So now let's try and slice this up. To remove the bottom half, all we have to do is put this diode between the non-ground wire and our oscilloscope signal input. This will only allow for the sine wave's peaks to pass through. And yeah, all the valleys are gone. Our signal now contains only positive voltages. Turn the diode around and everything will be flipped on its head. Instead of the valleys, we're now cutting out the peaks, so only negative voltages are passed. In theory, we now know how to get a positive, a ground, and a negative signal from our AC wall wart. But in practice, this is definitely not usable yet, because the voltages are fluctuating wildly. To fix this, we'll need to find a way to shape these curves into more of a straight line. Luckily, that's quite easy. All we need is a few big capacitors. For simplicity's sake, let's forget about the negative rail for a second and focus on the positive. Then what we are trying to do is keep the voltage here from falling. To do that, we'll have to divert some of the current whenever our diode is not blocking, store it somehow, and then release it when it's needed. And that's where capacitors come into play, because that's exactly what capacitors do. They store and release electricity. To understand how, let's go back to our pipe example. Imagine we attach a balloon to the open end of this pipe. Now, if we push water into the pipe from this side, the balloon will fill up and expand, effectively storing the excess water. And once the pressure coming from here drops, the balloon will release the water back into the pipe. Coincidentally, a capacitor works much in the same way. There's just one catch. For the balloon to be able to expand, it needs space to expand into. And the same thing's true for the capacitor. And that's why it has two leads and not just one. So while the first lead is the one we use to push electricity in, the second lead needs to be connected to ground, because that's where our capacitor expands into, so to speak. If we apply this to our problem, we get a solution that looks like this. Our diode is still blocking any negative voltages, but whenever a current does flow through it, our capacitors here will be charged, or filled up if you will. Then, once the voltage drops, the capacitors will release their charge, and by that, compensate for that drop in voltage. Think of them like a kind of backup battery for when the main power source dies. But just like a backup battery, our capacitors will need to be big enough so that they won't get drained before the main power comes back on. This, of course, also depends on the maximum amount of current we are pulling from this point at any given moment. But we'll get to that later. For now, we'll just assume that we picked the right sizes for our capacitors. Sadly, even then, we won't be able to eliminate all of the fluctuation from our positive rail. And that's because with every bit of water leaving our proverbial balloons, the pressure inside those balloons will drop. The more charge leaves, the less voltage we will have. So instead of a straight line, we'll read something looking more like this. It's what we call a voltage ripple. And voltage ripple is really not desirable for a power supply because it introduces noise and distortion to your circuits and makes components heat up. So we'll have to find a way to clean this up a fair bit. This is where voltage regulators come into play. They look a lot like MOSFETs, but serve a completely different purpose. You can feed them a possibly fluctuating voltage, and they will straighten it out for you, as long as that voltage is above their target. In this regulator's case, which is called the 7812, that target voltage is 12 volts. Sounds good so far, but is our ripple-plagued voltage even up to the task? Since the wall wart is labeled as 12 volts AC, you might think that it isn't. Because if our sine wave's highest point is 12 volts, then even that highest point will be below the needed 14.5 volts. Thankfully, that's not the case. For reasons that I won't go into here, a 12 volts AC wall wart will push out voltages ranging from minus to plus 17 volts. So we have enough headroom for a 7812 voltage regulator to operate smoothly, which should take care of our ripple problem. Setting it up is actually quite easy. There's 3 legs we have to deal with. The first one is the input pin, which will connect to our fluctuating voltage. Pin 2 needs a ground reference, so we'll hook it up to the wire we decided to call ground. And from pin 3, we'll get our regulated clean 12 volts output. But before we can see if that actually works, we'll have to talk about capacitor sizes. We said that choosing the right size for our capacitors depends on the maximum amount of current we'll be pulling. And now that we've decided to use the 7812 voltage regulator, that decision comes with an implicit limitation, because the 7812 is rated for a maximum output current of 1 amp. This gives us a good frame of reference to work with. Or let's rather say it would, if I knew how to calculate the required capacitance values. Sadly, I don't, so I simply did what I always do, which is Google searches and trial and error. What I found is that 3 4700 microfarad capacitors seem to work nicely. My PSU has never really given me any trouble. So that would be my recommendation here. Just make sure that your capacitors are rated for 35 volts or more, so we have some headroom there. And with that, our circuit would look like this. So let's find out if all of that actually works. First, I'll add in our 3 big capacitors after the rectifier diode. Then I'll place the voltage regulator and connect it to the capacitors and to ground. Now if I use my multimeter to measure the voltage at the regulator's output, we should see a steady voltage of about 12 volts. Looks good to me. Okay, so is our positive rail done then? In its most basic form, yes. But there's still a few refinements we should implement. While we successfully took care of the ripple caused by the slow ebb and flow of our AC wall wart, that doesn't mean we took care of all ripple in our output voltage. The thing is that our big capacitors are very good at supplying large amounts of current for a relatively long time, meaning they can eliminate low frequency ripple very well. But at the same time, they are horrible at killing high frequency ripple. And that's because the bigger a capacitor is, the more sluggish it will react to changing voltages at its terminals. Or in other words, a big capacitor can't supply current on the spot. It always needs some time to start pushing it out. Now imagine that the voltage at our regulator's input drops very suddenly. Why would that happen? Well, let's say that some of your modules suddenly try pulling a lot of current from your PSU. In turn, causing the regulator to instantly try and pull a lot more current from its input. Since our big capacitors can't react quickly, the voltage there is going to drop dramatically for a split second, meaning the regulator source of power runs dry momentarily. And that will cause a dip in voltage at the regulator's output every time the module's demands change, resulting in a very noisy power rail. What can we do to prevent this? You might be able to guess. We'll have to use small capacitors alongside the big ones. Additionally, we can choose a type of capacitor that is especially good at high-frequency applications, tantalum or ceramic, for example. As for picking the exact size, I've stick to trial and error one more time. 1 microfarad seems to work just fine. And again, the capacitors should be rated for at least 35 volts. Great, but where do we actually place these small capacitors in our circuit? There's 2 spots where they will be effective. First, very close to the regulator's input, allowing it to act like a high-speed, readily available buffer. So whenever the big caps are not able to provide current fast, this guy will happily step in. Second, directly behind the regulator's output, working like a sort of shield that can handle sudden spikes in demand even before the regulator has to deal with them. With this, our positive rail should be able to provide a clean and steady 12 volts. But before we move on, we should stop and think about two worst-case scenarios. First, what if we, while experimenting with our new power supply, accidentally create a short circuit somewhere? As we've designed it now, that would potentially cause our voltage regulator to burn out and die. And that's because the worst thing you can do to a regulator is driving current into its output. In what scenario would that happen? Well, imagine we accidentally short the regulator's input pin to ground. The output would immediately stop pushing any current out, making the voltage here drop to 0 volts. The problem is that our output capacitor is fully charged. This means that once there's no pressure coming from this point anymore, that capacitor will try and push its contents straight into the regulator's output, which we said is really bad. How do we prevent it? Easy. We just take another diode and connect the regulator's input and output like this. Since the output voltage is always going to be lower than the input voltage, no current will ever flow through that diode under normal circumstances. That's because the pressure coming from here is able to push the valve shut, so to speak. Only if we do short the input to ground, it will provide an alternate pathway for our capacitor to discharge through, since there is no opposing force anymore. And that's one fried regulator scenario averted. The other is much more likely to occur though. Voltage regulators generate a lot of heat during standard operation, because the excess energy created by reducing the voltage has to go somewhere. And the more current they push out, the hotter they get, until they reach a set threshold and go into thermal shutdown. Though they'll likely survive this, it's still not desirable. The solution is to simply attach a heatsink. You can get these in all sizes and forms, but a general rule of thumb would be the bigger the better. I use this size of heatsink, and I never had issues. To attach it, I first apply thermal paste to the contact area, and then use a simple screw and nut like this. Time to add the two small capacitors, the regulator with attached heatsink, and the protection diode to our breadboard. It's important that we place the capacitors really close to the regulator. This will allow them to react as fast as possible. Plug in the multimeter, and we should still read a steady voltage of around 12 volts. Looks good to me. So that's the positive rail finally done. Thankfully, the negative rail pretty much works the same way. Except we need to basically turn everything on its head. First of all, our rectifier diode needs to be flipped 180 degrees. This means that instead of the peaks, we will only be passing the valleys of our AC sine wave. It's like as if we are periodically sucking current out of our capacitors, and in turn, the voltage regulator. For that to work, we'll also have to flip the capacitors around, at least the big electrolytic ones. This is because they are polarized, which means that they really don't like it if the voltage on this terminal is higher than the voltage on this terminal, which is why they are labeled plus and minus. So in order to be able to suck current out of them, we'll have to orient them this way. Other than that, nothing changes. They'll behave the exact same way. Since I'll be using ceramic capacitors here and here, we won't have to worry about their orientation. Ceramic capacitors are non-polarized. Beware, if you decide to use tantalums, those are polarized. For the regulator, we'll use the negative voltage counterpart to our 7812, called the 7912. It has two slight quirks that we have to look out for. First, the input and ground pins switch positions. So this one needs to connect to ground, while this one gets the negative input voltage. Second, the 7912 does not need an output protection diode, because it has one built in. Quite handy. So I'll set up the negative rail on this other side of the breadboard. We'll create an alternate pathway for our sine waves valleys to travel into, using another 1N4007 rectifier diode. Then I'll add the big capacitors. Like I said before, watch the orientation. Finally, the regulator with an attached heatsink plus the 2 small capacitors. All done. Let's see if it works. And yeah, that looks about right. We get about -12 volts between negative and ground. Plus, we get about 24 volts between positive and negative. And that's all there is to building a simple dual power supply for your synth modules. Of course, you'll probably want to get this off the breadboard and into a more permanent setup. For that, I recommend checking out my video on how to build a triple VCO module. I'm going over the process of translating a schematic into a stripboard layout there. Also, I've added the full bill of materials, plus a few shops that sell 12-volt AC warts to the description. Hope this was helpful. If you enjoyed this video, consider supporting me on Patreon, and I'll see you in the next video.